Hello, this is simply about networking protocols, and today we will talk about multicast and perform multicast overview. Standards that describing multicast, how it forms, how it's used, specific addresses per protocols and networking functions are on your screen. There is much more. I recommend to start with RFC 1112. In this video, I'll talk about multicast role and tasks, L2 and L3 multicast, control frames multicast and data frames multicast, multicast group basing on HGMP example, and rendezvous point basing on PIM example. So, what are roles and tasks for multicast? Let's imagine that we have a topology where an end station supposed to receive some specific traffic, and this traffic has information that is same. Internal information, is same for each endpoint. In this case, internal structure of each frame will be copy-paste, and only some external fields will differ in order to deliver specific frame to specific station, right? And if we execute this function as is using unicast, then we supposed to generate from the source as many similar, absolutely similar frames, copies of the same frame, as many end stations supposed to receive this frame at the end. That is overload of the system generally, and we would wish to simplify this and find a mechanism of using single frame in single destination if possible. It means that if we have one link and through this link we need to send same information to as many stations as possible, it would be good to use single frame to send this information through the single link. And actually this function is executed by multicast. And how multicast differs from broadcast? Well, I'll talk a little bit later. We have a source, we have desired destination, possible destination. We have possible destinations. But not every possible destination would desire to receive this traffic and would need to receive this traffic. Imagine it as radio translation or some internet translation, Twitch, YouTube, whatever. So at the same time, single unit of the information is being generated and sent, but many people would like to see it, and even more people would like to not see it or hear it. Okay, so we need to distinguish who would like to receive this information and who would not, right? And this mechanism also is implemented using multicast. In general, multicast role is to receive a frame, to multiply this frame in as many copies as needed, and to send this frame through the interfaces that need to receive this information further. When we're talking about L2, right, as you remember from video about switching, it's pretty simple to implement because we can send a frame if there is no FDB entry in the for this destination, and it cannot be FDB entry for this destination because it's multicast destination. Then it's frame flooded through the all interfaces in this VLAN, so nothing complex, but still. And when we're talking about L3, it much more complicated because each L3 interface represents different subnets, so they are isolated from each other, and simple flooding wouldn't work. By the way, you remember this from video about MACs and IPs, but anyway, those are signs of multicast frame. For L2 and destination MAC, sign of multicast frame, this first byte is even, right? It's 01, 03, 11, 15, whatever. So we don't use odd frames. For L3, we have a range of IPs between 224 and 239 that are multicast IPs. So everything beside that is group ID, or this is group ID, this is not a host ID. And for IPv6, this is FF and then group ID. Group ID can be also used to identify some specific protocol or specific packet, control packet in specific protocol or networking function as well. And talking about control multicast frames, by the way, this is why we need multicast, or multicast is better than broadcast, because broadcast has only one address, and thus we can only allow it to pass or block it. In multicast, we have range of addresses, and we can allow some, block some, build a mechanism of building multicast group for some addresses and forbid for another. This allows us to process huge amount of different streams, multicast streams at the same time. Broadcast would not provide this possibility. In control multicast frames that are control for multicast routing, for multicast, some processing, for many protocols, we have control traffic that has multicast destination addresses, either L2 and L3. Well, if we have multicast L3 address, we would expect that L2 address or destination MAC will be multicast as well. But anyways, control traffic processed in the following way, mostly. We receive control frame, it is being captured to CPU and sent to our system for processing. Our system processes it, performs some necessary configurations, some necessary actions, and in case this frame needs to be sent further, system generates necessary amount of copies of this frame from our name now. As source, our system source MAC and source IP will be used, if it allowed. So it generates necessary amount of copies and sending to the frames. Behind those frames, we expect another systems and devices that would require this information from this control frame. Okay? For data frame, it's much simpler. We have, well, actual mechanism could little differs depending on is it switching or routing, is it IPv4, IPv6, is it which protocol is being used to organize the multicast routing on L3 level. But in general, actions are following. We have some table of groups membership where we noted all the members of the specific group identified by IP or MAC, and for this group we know behind which interfaces on our system there are receivers that wish to receive multicast traffic identified by this group ID. Receiving some data frame, we're taking information from group membership table, multiplying this frame as many times as needed, and sending through the interfaces behind which we know there are stations that requested to receive this multicast traffic. Let's take a look on this procedure and how this group's membership is formed based on AGMP protocol. So source generates query. This is not a request, this is query. This is informational frame that claims that source will generate multicast traffic identified by some specific group ID. Our system receives this frame, sends it to CPU, this is control frame, remembers behind which port we have source of the multicast data, and sending this query, regenerating and sending query to all possible to all devices who possibly could be interested in receiving this information further. This is, by the way, the first level of the filtration for multicast traffic. On some interfaces, multicast could be forbidden, and this information will not go further, and no multicast traffic will run through those interfaces. This is one. Devices that received those queries at some point decided that they are interested in receiving such an information and replying with join packets, saying that they would like to join this group. They would like to set up a membership in this group. Again, this is control traffic. It's being forwarded to CPU. Our system remembers behind which interfaces those interessants are and adds this information into group membership. So group membership is specifically saying that behind interface 1, someone who is interested in multicast traffic identified by group ID 1. Also, we are sending join from our system towards the source, saying that, yeah, we are interested, I am interested in receiving this multicast information because there is someone who wants to receive it through this device, so this device needs to receive it too. Unfortunately, or fortunately, depends. Then when data traffic is coming, data frame also has identifier of group membership. We are comparing which interface behind which interfaces there are interessant in this traffic, multiplying frame as many times as needed and sending it through those interfaces. That's how it's simple is. In basics. Details could add some additional headache, but in basic everything is very simple and straightforward. Let's take a look on that schema on that process on the bigger schema. So there is a source who generates the query. Query goes to some intermediate router. Router receives this information, reminds itself that source behind this interface, and sends queries to all other interfaces where possible interessants are. And this happens on each router step by step. So this procedure is universal for all devices on the path. End stations who decided to receive the multicast traffic identified by specific group ID sends joins. Those joins are collected on each router, multicast router, in the way I described above, and goes back to the source. So source now knows that there are at least one interessant and starts sending multicast traffic. everybody's happy. Now talking about rendezvous point. Well, when we're talking about multicast, it very depends on configuration. And it is possible that source will be somewhere not close to us, and traffic needs to pass some external network where we don't know the configuration there. And this network and configuration there could cause chaos. To avoid this chaos, we can see that this is the device where we need multicast information in the first place. There is no any other point where this multicast traffic can go before reaching this device. So we claiming this device and point of rendezvous or rendezvous point, whatever, and to avoid any misconfiguration in external network, we can send our multicast frame wrapped into unicast. Unicast destined to our point of rendezvous or rendezvous point, whatever. It will reach our rendezvous point as unicast. There will be unwrapped and now will be processed as multicast and will perform all multicast actions starting with all necessary information and so on. This is the mechanism described in PIM specification, in PIM-RFC. That how simple in general to work with multicast and how it works. There will be additional complexity when you start looking into specific protocols because, well, those are actual protocols. They need to cover as many corner cases as possible. But in general, idea is like that, and it's very simple. Thank you. Have a great day.